In the Khan Academy video, it was shown that if you have a region that looks something like this, so this is our region and it's enclosed by a curve, and the curve is drawn, oh, that was the wrong way. The curve is drawn so that as you walk along the curve, the region is to the left. And you have a vector field. F is a vector field given by m of xy plus I plus n of xy j. Then we have that the integral over c of f ds is going to equal the double integral over the region of the partial in respect to x of n minus the partial in respect to m of y dA. Now, there is a slight problem here. What we did was really nice because I was able to break this up in two different ways. I was able to break it up so that I had two curves that were functions of x, and also so that I had two curves that were functions of y. But what if I had a region that looked something like this? I can still break it up into two curves. Let's orient it just so we're all good there. I can still break it up into two curves that are functions of x, but I run into problems if I try to write curves that are functions of y, because you'll notice that it fails this horizontal line test. So I can't break the curve up into things that are functions of y. So the previous argument didn't work. What I'm going to want to do is I'm going to want to split the region down the middle so that I have two regions and two curves, each of which can be split up that way. So just to be really clear what I'm saying, I'll have one region R1, which is enclosed by a curve R1 that looks like this. I've added a little bit to the boundary along that split. And then I have a region R2. And again, I've added a little bit to the boundary along that split here as well. And you might notice that the boundary is going in different ways, which is going to be really important soon. So what can we say about each of these sides? So let's call this C2. So what can I say about the integral of R, saying that R is the union of R1 and R2? I can certainly say that the integral of R of nx minus my dA, that is certainly going to be the same as the integral of R1 nx minus my dA plus the integral of R2 of nx minus my dA. Can I say the same about the curves? What can I say about the closed curve of C of f ds? Well, actually, let's go ahead and see what happens if I add the curves together. If I add together the curve of C1 of f ds plus the curve of C2 of f ds, I notice that I have my original boundary plus some extra stuff. So I'm going to call the original part of C1, I'm going to call that C1, I'll call it, C1 star. And then the new part, I'll call C1N, just for new. That's horrible notation. And we'll do the same thing here. We'll have C2 star, that's the original. You know what, if we're going to call it original, let's just call it like O with a cursive O or something. C, O, and then C new. Okay, cool. This is going to equal, well, that's going to be C1, the old part of F, plus C1, the new part of F, plus, and I'll write this in the other order just for reasons, C2, the new part of F, plus C1, the old part of F. And what we'll notice is that the new part of C1 goes in the opposite direction as the new part of C2, but otherwise they're tracing the same paths. So these trace the same path in opposite directions, so they cancel. Okay, let's give ourselves a little bit more room. Therefore, this is really just going to be the old part of C1 plus the old part of C2. Oh, C2 old. Don't need a subscript there. The old part of C2, which will end up equaling, well, if I put C1 and C2 together, they will end up equaling my original curve, C. So if I put the two old parts together, we get the whole curve, and that is exactly what I want. So what does that tell me? Well, by Green's theorem, by the part of Green's theorem we already proved, we have that the sum over the region 1 of nx minus my dA equals the sum over C1 of f ds, because that is one that I can break into two parts, one which is a function of x, one which is a function of y, with a slight, is that really a function of x? Up to you. In hindsight, I figured that it was a little too important to talk about this vertical strip nonsense than to just leave it, under the rug. So we're going to talk about how we can adjust the Khan Academy proof that we saw to accommodate having vertical strips, which aren't exactly functions of x. So I'm going to do basically the half of the proof where we have our horizontal component of our vector field, so our vector field f. We're just looking at the horizontal part, so we're looking at m of x, y, 0. And again, that's just the component we're looking at for right now. So I've written out what I have here. So I can break the curve into three parts. I have this bottom part, which is a curve in respect, or as a curve, which is a function of x. I have this top part, which is a curve, which is a function of x. And then I have this vertical strip, which isn't a function of x. So let's see what happens. So I'll split my line integral up into three parts over those three curves. The first curve I can parameterize as x equals x and y equals alpha x. So, and my x values are going from a to b. So to evaluate this integral, I do the integral from a to b of, I would do my vector field composed with my parameterization, which is going to be m of x, alpha of x, 0, dotted with the derivative of my parameterization. I don't really care about the second component for reasons you will see soon, because when I dot these, all I'll be left with is mx alpha x dx, because this will just be plus 0 times whatever the derivative of this is, which I don't care about. So I'm going to kind of just ignore that I wrote that. This is really the part that I'm interested in. So I'm going to do that. The second part will be very similar, so I'm not going to go through and write the vector field part out. But what's different is that this curve is being traced backwards from b to a, so I could write this. Since it's the opposite of the path from a to b, it's going to be negative the integral from a to b of m of x alpha or beta x dx. And what's this last part? Well, essentially I'd be taking the integral from a to b of my vector field, which is m of, I guess I'll call it bt because I called things different here, times the derivative, oh sorry, it's not just bt, that's just the x component, the y component 0. And I'm dotting that with the derivative of the x component of my parameterization times the derivative of the y component of my parameterization. I should notice that these aren't actually a to b. They're actually totally different values. I'll call them c and d, but I will fundamentally not care what they are. Because when I actually do this integral, it's going to be a really interesting integral over the function 0, which is going to be 0. So this whole part goes away. Then we can kind of proceed with the Khan Academy proof, do some rearranging. I'll flip the order, negate some stuff. So this is going to end up being negative the integral from a to b of m of x beta x minus m of x alpha x dx, which equals negative integral from a to b from alpha x to beta x of the derivative in respect to y of this function, nxy, which will end up being the negative integral over our region, because if we look, our region is exactly bounded by beta, alpha, and then these lines AB. So that'll be the negative double integral of our region over the function dy, which is exactly what we wanted for this step of the proof. The alternate step of the proof would do the same thing in regards to like horizontal lines, so we wouldn't need to worry about those. And from there on, we'd be in business. So you can deal with these vertical and horizontal strips without the universe imploding. Now, granted, there are still parts of this proof that we can't fully deal with, and we'll get to that at the end of this video. But this is a part that we can certainly handle using what we know now. So we have that. And then, on the other hand, we have that the same thing is true for regions 2 and since we showed that when you add up R1 and R2, you get the integral over R, and when you add up the integrals over C1 and C2, you get the integral over C, we therefore get that the integral, well, we'll write it in the right order, we'll get that the integral over C of f ds equals the double integral over R of n x minus my dA. Okay, now there's one last caveat, which we won't actually fully address. Um, First of all, we showed when we split it up into 2 regions. You can certainly do more than 2 regions. That won't necessarily break anything. Yeah, you can use that same argument to show that all of the kind of places where the boundaries overlap of those different regions, like for each region that you look at, there will be, or for each pair of regions that touch each other, there will be a little boundary line, and those boundary lines will cancel each other out. So that will happen no matter how many. We just did it in the case where there's 2 regions. You can certainly do that with more regions, splitting it up into more regions. This argument does extend nicely. But what if you can't split it up into a finite number of regions that are nice? What if we can't split it up nicely? Well, the idea is you have a sequence of approximating regions. And those that are nice or can split up nicely. And then you take the limit as our approximations get closer. We're not going to do that. But there is a nice way to finalize the proof if you do all of that jazz. So there you go. There's kind of the last steps you need to prove Green's theorem.